happy to be here. I was talking with some of the speakers yesterday, and yeah, I realized that, again, I confirmed again, that there's a lot of confusion between the products that we have at Polygon. So I will try to add a little bit more of more confusion to that mess. No, I'm joking. But I will try to explain. As I am engineer, but I am very product oriented, so I will try to explain a little bit. How these two products, Polygon Edge and Polygon Zero, fits inside the Polygon product range. So this is the topic we are going to talk today. Polygon Edge, tracing for Polygon Zero, but starting with who am I? I'm Víctor Castell in most of the social networks. I'm senior engineer at senior blockchain engineer at Polygon Labs. I have this side project called Linktree that is a distributed fault-tolerant cross-job system written in Go, and also XK6 Ethereum. That is an extension for the K6 load testing tool. It's a DevOps tool to perform load testing. It can be used to load test EVM-based blockchain clients and also master artists and CMP. So if you want to talk about blockchain topics or any other topics, just reach out to me. I will be happy. Okay. Well, my story, I joined, or the two stories team, right? I joined Polygon to lead the infra team a couple of years ago. But then soon I realized that I wanted to do full-time Golang development due to my experience in previous experience in Go. So I was third and I jumped to the V3 team. What was the V3? No? Then SDK, then X, then Zero, because the next, then the mesh. V3 was a fork of Geth that we were working on at Polygon. The goal of that fork was to implement IDFT consensus with instant finality to create a client that can be used for enterprises, basically, for creating POS networks. I joined that team. Then at that time we had, at the same time in parallel, we had what was called the Polygon SDK. Polygon SDK was not a fork of Geth, it was a full-fledged Ethereum client implementing an IDFT 2.0 consensus path, but with POA, proof of authority at the time. And that, at some point, Polygon decided to deprecate the V3 project and rename the Polygon SDK to Polygon Edge and integrate the consensus that we have been working or building on top of Geth for V3. We decided to implement it using the Polygon SDK or Polygon Edge. That was the name of the Polygon Edge. I hope that brings some clarity to the theme. Later, in the latest months, we iterated with Zero in the latest months. Zero is I will talk about that in the next slides. So Zero was based on the work of Mint Protocol. Mint Protocol was a group of engineers that created this Zero knowledge proof. Actually, this library Plonky 2, as far as I know, it's able to create fast recursive proofs, ZK proofs, right? And that was the Mint Protocol team. So I will circle back to what's Zero in the next slide, but for now, what's Polygon Edge? Polygon Edge, in its current state, is a Supernets client. Supernets will be like the protocol, so it will be Ethereum in Ethereum, and the client will be Geth or Polygon or whatever other client. So the protocol is Supernets, the client is Polygon Edge, like it's written in Go. It's an app-chain solution for enterprises to build proof-of-stake networks with custom configuration and rules, kind of, I don't know if you know, Supernets for Avalanche, something kind of similar, but not really the same. The protocol is based on IDFT 2.0 with instant finality, and it's again full 100% EVM compatible. We can deploy any contracts for Ethereum. And it has a native bridge implementation, so it's tied to a root chain, and the bridge protocol is implemented into the client. It's not any other piece aside from the client, right? So, the staking for the proof of stake or validators is based on the root chain, and at this time what we have been working on is to integrate edge and zero, so we can use now zero to verify transactions and blocks efficiently. Okay, so what's Polygon Zero? The Polygon Zero is one of the ZK pieces that Polygon has, and it's based on from key 2, zero knowledge proving library. It's a system to generate ZK proofs based on the Proving 2 library. It's a ZKVM based on the work that they did on protocol, layer 2, regeneration. Yeah. Now, zero means edge. The thing is that zero doesn't have the necessary infrastructure for accepting transactions and blocks. So it needs kind of an infrastructure around it to accept blocks and transactions. No? It needs an RPC endpoint or an RPC system, a transaction pool. It's basically a sequencer, no? Or in this case, we will use Edge as a network of validators that accepts transactions and store transactions in its blockchain, and Zero will use the Edge to query those blocks when it needs. Actually, this is how it looks. We are going to focus only on this part. This will be the zero prover architecture. It's a little bit of high-level design of the architecture of Zero, but yeah, we are going only to focus on this communication part and this piece that will be Edge and layer 1. So, what's the mechanism? Zero will have a smart contract deployed on layer 1, the checkpoint reach contract. It will query the latest block proof, the latest checkpoint, the latest block proof, and get a specific key, and it will query them or wait for blocks starting from that key. We'll wait for blocks generated in this network, right, in the Edge network, and query them by gRPC. This is the basic system. Then it will basically use do its work inside this, but we are going to treat this as a black box. Yeah, in this presentation, so no need to go into details on that. Anyway, so we needed a protocol for integrating both components, both systems, Zero Prover and Edge. So we went for a straightforward implementation using the RPC for communication between those two elements, and we used JSON format for JSON structure, segregation structure for exporting the fields that Zero needed for proving blocks and transactions, right? This is, maybe I didn't mention it, but this is the second part. This is where we get technical in the presentation. So starting with the code, this is the gRPC interface. It's very simple. It's just a getTrace method that returns a getTrace response. The request will accept, so the function, the RPC endpoint will accept a block number and will return a chunk of bytes that will be the block trace, so the serialized block trace, right? Just in bytes. So the client will be responsible of serializing that trace and the JSON data structure. We are going to need to build the trace, right, in the client in Edge. So this is the steps we are going to do. We are going to receive transactions, or in this case, Edge is going to receive transactions. The network is going to receive blocks and validate blocks, and any given client of the Edge network can receive blocks using its fields, can receive its neighbors, or if you need a proposer, it will execute the transactions received, and it will run some EVM hooks at the EVM level. This is where we are going to track the delta. I will stop here and I will explain how we track the delta in events. Right? For you to have an idea or a schematic idea of what the traces are, or that what we wanted to achieve. So we are not sending with every trace. We are not sending the full state to zero. We are only sending only a part of the state. Actually, the subtry needed to execute those transactions, right? The transactions in that block. For example, here's a clear example. In transaction 1, Okay. In transaction 1, we basically read this account 2. We're going to read this account in this stride, and from account 1, for the storage stride of account 1, we are going to read the value. Okay, that's the first transaction. That's only this. Transaction 2, we are going to add one value to the storage stride. Write one value to this account storage. Okay. And in transaction 3, we are going to update this value to B2. The same value, we're going to change it because transaction changes. So for the pre-state, we are going to send the value. The pre-state it's like that, right? It's what was the state try or the partial state try for executing this that this transaction needs to execute. We don't need this value because this value is being written in this transaction, so it's new. So we are not sending the pre-state. But this transaction needs to read those values, so we are sending them in the pre-state. Okay, I think, hope it makes sense. Okay, the commit stage. When we execute the EVM operations, right? We generate the data traces. The data traces on each EVM operation. So if we do a memory read or a storage read, we are going to trace that operation in order to send to the trace that action in the final trace. If we are going to read the balance or change the nonce or update the nonce or whatever, if we touch the account, we create an account, we deploy a contract, that will be written through the trace on each operation. Tries are composed at the time of accessing the storage, and when the state transition function is being executed, it's going to create those traces. How those traces look, right? For each trace, or not for each trace, but there are entries in the journal. We are going to use a log type structure, a journaling, right? So this is the Polygon structure that contains a journal entry. It contains the address. This is the account affected by this change. It can change the balance. It can change the nonce, and this is important. It can update the storage, right to the storage. If it's stored here as a map of hashing of hash and keys and values and hash, it can read from the storage. That's important because we are going to store the changes in this the reads of the storage in this variable in this structure. If we deploy the code or if we read the smart contract, it's resigned as or read. Okay, tracking those changes, it happens in this function in code. So every time an EVM operation is performed, okay, we are not tracing. We are only tracing state changes, right? We are not interested in math operations or whatever other operation. Only state changes in this case. We are going to track account change with the address that is changing, and we are going to create a journal entry. If it's an unchange, we update the nonce. If it's code deployment, change the code, balance, etc., or any of those fields that we have seen. How they look in JSON. So this will be rendered to JSON. As you can see, these are the meta instructions that allows Go to Marshall to JSON easily. We are going to send the parent state root, so the root of the hot try for that block, and an array of transaction traces, right? The transaction itself are be encoded. The delta, and this is going to be one of the delta changes in the transaction. So we call them delta. Those changes, different traces that we generate for each EVM operation, we call them delta changes because it's the difference between the pre-state and the final state. So at the end, performing, also applying all the data using the pre-state, you should be able to generate the final state right. Zero prover should be able to generate the final state right and check if it's correct using the final state. So this will be the address access. And we will have a series of key values here for the storage. In this case, it's the storage read, the storage write. Sorry. So the values introduced into the state, and we will have another piece here for the storage read, the value accessed by this transaction. Okay, this was for tracking deltas. Now we need to build the whole trace, the whole thing, and store it in JSON. These JSON files will be read by the gRPC service in Edge, and will be set by Edge, and will be set by gRPC. So it's going to read those traces from the tracking. Yeah, as you can see, as we are going to generate those traces from seeking blocks or proposing blocks, any client will be able to generate traces. So not only the validators or the block proposers are going to be able to generate those traces, but almost they have those traces, because at the time of seeking blocks, they are going to execute transactions and generate the traces anyway. So composing the final trace will be composed using those JSON fields. This will be the data structure for the trace. We'll have the transaction and the delta, as we have seen in the previous JSON file, the receipt root, transaction root, hash, and let's scroll down a little bit. The gas used and the root filters. The gas used is within this transaction. This is a trace for one transaction. This is the full trace. Yeah, in the full trace, what we need to send is the pre-state that I mentioned. It's the account type and the storage type, key values. With this is the structure that will end up rendered to this. This is the array of transaction traces shown in the previous slide. So this will generate an array of transaction traces that will get stored here, and the account type will be this hash, this key value store of the tribe of accounts and storage tribe. Usually, this is the world state tribe. It's always a full set, but Zero Kubernetes has to separate those two entities. I'm not sure why, but the account tribe separated from the storage tribe. So here in the account tribe, you will find the accounts accessed used during the execution of the transaction of that specific block. And in the storage tribe, we will find all the values accessed, read from those accounts during the execution of the transactions of that specific block. And this JSON file, the final transaction, the final trace, is generated in the disk. So it's stored, written to this. At the same time, that block is being, that block is saved to the local DB of the client. This is a pre-state as a representation of the world state tribe. And I already explained this. It's a hash. It's a key value structure with accounts and storage used in the execution of the transactions of that specific block. Okay. So a little bit of wrap up. Here we have shown how we can combine a proof of stake network and send block traces and information to a zero knowledge type 1 system that is zero. So it means that zero is, according to Vitalik's classification of ZKVMs, zero is a type 1 system because it's fully compatible. It should be able to verify blocks even from Ethereum mainnet, but also from this custom POS chain. So it can verify full EVM, 100% compatible with the EVM. For that, we are treating zero as a black box system in this case because we don't need to know the details of what the prover is doing. We are implementing the changes on the side of the client, and it's pretty general. No, we hooked it into Edge, but it can be hooked into any blockchain client. Actually, I think we are going to do it. And it can be your custom rollup. I don't know, Optimism or whatever, Stack using Stack or whatever. So mainly, you should be able to convert stack-based rollup into a CK rollup, that will be great. Anyone here for whatever. That's it.
So sorry if I start a little bit high level. I hadn't heard of the products before, so I may be a little bit lost here. The proofs are being generated basically on the Supernet itself, right? And then you just obtain it to zero, and then the send that stored somewhere.
No, actually, it was showing the slide.
Yes.
I'm going to show it. The proof is generated on zero,
yes.
on the prover. Okay. This is the prover system, and it's basically sent to the contract one.
Okay, so is the where are the proofs? Where do the proofs end up being stored? What's provided data related for proofs? Is that being stored in the data one itself?
Yeah, I think so. Yeah, the proofs will be going to be stored in data one.
Yeah. Okay, thanks. And I'm curious more about the usage of this. You said this is focused on enterprises, basically. So
actually, Polygon X is like the client focused on enterprises, like having some enterprise features like access list and things like that. That was Polygon X. But yeah, as I said, you can use any browser for this matter, right? So it's not tied to this specific type of client or network. You can use anyone, whatever.
Thanks.
Yeah. Thanks.